Welcome back. In the previous couple of videos, we talked about the SVM concepts, the linear SVM classification, the polynomial kernel, and finally now we are going to cover the Gaussian radar basis function, RBF for short. Now I've provided the actual kernel function and the mathematical function here, but I won't be going through them. In essence, really the whole basis of the whole point of providing them here is just so that you can see that linear is just basically like that. Polynomial has a degree here. If it's 2, then it will be quadratic. If it's 3, it's cubic. And then there is actually a coefficient to go with it, which is the basis function. And then the RBF here is an exponential with the gamma in front. And basically the whole thing is actually absolute or square. Right, so we're gonna again repeat the whole exercise here. So since it's the same, I won't repeat myself. What I will do, however, just to cover this, the C is equal to 1, and the classification we now specify RBF as our kernel, and the gamma we set at 0.7, C is equal to 1. We're gonna fit the scaled X train data with the Y train. Now we're going to run the cross validation within the trained data set. You can see the accuracy is 95. It's not too dissimilar to the linear. If you recall, the linear was, let's have a look, 95.01 and 5.38%. And if we look at the RBF, yes, it's actually, well, funny enough, it's the same. But that's okay, that's quite normal. You can see that there are 5 errors and the confusion matrix. When we actually run the precision score, it's 95.86. It's actually the precision score and the recall as well as the F1 score. These are all better than the linear function. Okay, so these are all 95. This is 95.01 and 5.38. Okay, right. 95.01, 5.38. Okay, now we're not going to stop there. Remember what we covered in the past when it comes to the whole workflow of machine learning. We split our data into training set as well as the test data set. Within the training data set, we use cross-validation to improve our model. And rather to cross-validate our model, first we train it and then we cross-validate it either using 3-fold or 10-fold. 10-fold happens to be the quite popular one. Now there is one more step that I have not covered, which is called grid search. I'm going to show you how grid search is done now. The purpose of grid search is that using the existing training data, we're going to continue to optimize and find the hyperparameters that actually will provide the optimal or the best parameters so that the SVM will perform the best amongst all of the different possible combinations of hyperparameters. So what we are doing here is import the pipeline. Again, we perform the test, train test split, and we're importing grid search cross-validation. Of course we can, there's one step here that I have not done, which is scaling the actual features itself. We're using pipeline here, providing CLF, which is our classification function, and then we set to kernel, it's the RBF, C is equal to 1, gamma is 0.1. Now this is the parameter that we want the grid search to scan through. 0.1, 0.5, 1, 2, 5, 10, and 20. And for the gamma, 0.01, 0.001, 0.1, 0.1, 0.1, 0.25, 0.5, 0.75, and 1. So essentially what you have is 0.1 to this, 0.1 to this, 0.1 to this. So it's actually many combinations here. Right, in terms of the grid search, this is how you set it up. You provide, in terms of the input parameter, the pipeline, which is this here, and the parameters that, the so-called parameter we wanted to sweep through, the end drops, basically using all of the CPU cores, cross-validation of 3, and we are scoring it using accuracy. You can actually change this to other that's relevant for what you want to do. And we store the result into SVM, the grid search RBF, and we're using that to fit our train, and it's going to run for a while, and we print out the actual test score. So it took for around 5.3 seconds. It was running parallel jobs, so that's why it actually was quite fast, although there were actually a lot of parameters to sweep through. And what you can see here is that the actual best accuracy score is 95.83. It's actually an improvement to the 95.01 that we were looking at earlier. And the best parameters is actually, let's just print it out, is when C is 0.1 and the gamma is 0.25. Okay, so having found the best parameters, hyperparameters, we are now going to take a step further. Let me just add a description here. Conducting validation in the test data sets. Okay. Now this is not for tuning. This is for the purpose of us getting a rough idea how our model will actually perform in the real world data, or data that has not seen before. Notice that we did all of our so-called training using the training data sets. We haven't exposed it to this test data. This is what we're going to do right now, and let's have a look at the confusion matrix. And voila, what you can see here is that it's perfect score. All right, it did not actually make any mistakes at all. And then when you actually look at the precision, the recall, and the F1 score, they are all perfect. Well, I don't know if you can improve on that anymore. Well, I was going to ask you to do an exercise on this. Probably the one exercise I'll ask you to do, because obviously you can't actually perform tuning on what is already perfect. So what I'd like you to do is actually do this one variation. Change the training set to 60%, meaning convert this to 60. And try to see whether you are still able to achieve perfect prediction out of sample. So with that, I'll ask you to actually pause the video. The whole purpose of that is just so that you can actually walk through the steps and be familiar with it and be comfortable with it. Okay, so when you come back, I'll wrap up the lesson and also cover through what we are going to look at in the next lesson. I hope you enjoyed that exercise. It was an interesting one, definitely. So I think it's probably pay for me to actually at least try that since we have a bit of time. Let me run that through. It won't take very long. So the accuracy score is 97. Okay, it's actually improved, interestingly. Let's run a grid search. And let's see what the best score is. Alright, the best score is 97. And let's have a look at what the out of sample looks like. Well, it gives me an inconsistency number of samples error. Let me just have a look. Well, good thing I run that, and what I found is that there was an error in my code. I store it in the x underscore std underscore test. You need to change it to x test. Looks like what we ran earlier wasn't fully correct either. That probably explains why it's 100%. And when we actually convert it to 60%, I'll come back and run 80% in a minute. When we're looking at the 60%, what you can see here is that the average accuracy is 97. Actually is higher than the linear already, and the precision score is also higher. When we conduct the grid search, the best score is in terms of accuracy is 97.77. So it's actually a marginal improvement to the original score. And in terms of the out of sample, and what you can see here, it's a respectable 93% in terms of the precision score. So let's come back here, and I'm going to change it to 80% now, and rerun all of these. 95.01, so that's the same as before. Let's see if our grid search, what kind of best score can we get out of these? Should be the same as before. Yep, 95.83. Let's run in terms of the confusion matrix. Okay, fair enough. Alright, so this time around, even though I've changed the actual so-called tests, it still actually get a perfect score. So obviously it's actually done, it still actually has been able to actually segregate that really well. Well, obviously that was quite interesting. So what I did do is that I've added another 2 line of codes. What I wanted to do is actually just to plot it out. Of course, these are still the so-called train scores or train data, and what you can see here is that it does have some errors, but generally it's pretty good. So that's really at the end of the lesson. What we have covered in this lesson is the RBF, and what we've gone through is just the same process, which is fitting it, of course using the scale data, and also conduct cross-validation. We also perform the grid search, but within the grid search there's one step that I've left out. I would encourage you actually to try that out, see if the scaling actually will improve the overall scores or not. Remember, it should, because knowing that SVM is really sensitive to the scaling. And we conduct the grid search, find the best parameters, and interestingly it gave us a perfect score when it fitted to a never seen data before, and we plot out the actual the so-called separating line. With that, I'm going to end this video. When we come back, we're going to apply this support vector no longer to classification. In the next video, we're going to apply this to regression, and let's have a look, see how it performs in regression settings. I look forward to seeing you in the next video.